test ahead of time what you're going to do. Prepare ahead of time before you film. I had students last semester who would do the experiment while they were filming. That's really not the purpose of the video report. You want to do the experiment first. It doesn't take very long. And then figure out how you're going to record the video demonstrating the phenomenon and explaining it. Because otherwise it's going to make very long time. It's going to take very long time. Okay. Yes, Chase, I do want you to show your face in the video. If you didn't show your face in the video, I don't know if you can add to the end of the video or something, so you'd have to remake it. I don't know how long your video is, but ideally, I really want to see you in the video, just because I want to know it's you that did the lab. Okay. All right. So what I'm going to do is start talking about properties of the charge, and then in lecture, I will talk about, today I'll talk about Coulomb's law and the electric field. So the first few slides I'm going to go through I've taken them from the lecture slides just so I can go over them, and then I can start on Coulomb's law right away in lecture. Okay. So far in this course, you've talked about, oh, not this course, but so far in your experience with physics, you've talked about fundamental measurements such as length, time, and mass. Are you all familiar with these? And I call them fundamental because you can't derive these from anything else. You cannot derive these measurements from anything else. Okay? And of course, there's units associated with them. And if you've had Physics A with me, you know I go through this. So we're going to introduce another fundamental measurement called charge. And so I want to spend a little bit of time talking about charge. And we use the letter Q to denote charge. Sometimes capital Q, sometimes small q. We're more particular using the small t for time because temperature is also another fundamental quantity you will learn in Physics 215, or you might have learned it in chemistry already. Okay. So the question is, what is charge? What are its properties? And that's what I want to start with today. So let me start by saying a couple of things about the history of electric attraction. I'm not going to go through it in details, but I have there like a little list of the history. Franklin, who's known for his work in politics, is also a scientist. He came up with the idea of plus and minus type charges. And Dufay and Franklin, around the 18th century, they noticed that if you charge two things the same way, the materials will repel each other. If you charge them differently, then the materials will attract. So what do I mean by that? So let's say I take a PVC rod. This is part of your kit. I hope you all got your kits already. Okay. So this is a PVC rod and fur, and I rub the PVC rod with fur. If I do it to a second PVC rod, I do the same thing to the second PVC rod, and I bring the two rods together, I will notice they repel. In fact, if you take the fur, the two pieces of fur that you use to rub the rods, you will find they would repel too. But the fur and the rod would attract each other. So there's two different types of, and the term they used then was electrification. And this led to the idea of plus and minus charge by Franklin. Now, this semester, we're really going to be working with the PVC rod and fur more than anything. We can charge things positively by using silk and glass, but I found last semester that the results for the students was not very good. So I kind of stayed away from you guys doing experiments with the glass rod and the silk. If we were on campus, I can come there and help you make it work. And usually what happens is when you're on campus and you need help to get something to work, and I show you how to make it work, you'll get it to work. So it's much more difficult to do it online. So I kind of remove that part of the lab where we're using glass and silk or glass and wool. Okay. So when you notice on that list that, Franklin also introduced the idea of conservation of charge. Thomson measured the charge to mass ratio of the electron in 1897. And I will say something later on this semester about the Thomson measurement. And then Millikan showed that charge is quantized, meaning charge comes in discrete values. Okay. So here's some basic properties of charge. First of all, charges exert forces on each other. They either attract or repel. This is different than with masses. Masses will only attract each other. And what I'm talking about involving mass, that has to do with the gravitational force. Okay, the gravitational force has nothing to do with plus or minus charges. Okay, at least to our best knowledge, our current best knowledge. Okay. Charge is a scalar just like mass. It's a number. It's not a vector, it's a number. Charge is conserved. Now, charge can be positive or negative. The basic unit of charge is the charge on the electron or the charge on the proton. And so the charge on the electron, I'll write Q sub E, Q for charge, is minus 1.602, and I'm only writing it to 4 significant figures, times 10 to the minus 19 coulombs. And for the proton, those are the most basic unit of charge. All other charges are some sort of linear combination of those two. The neutron has no charge. Now, I want to say one thing though. We're going to ignore the concept of quarks. Okay, we know that there's quarks. We've never isolated a quark, but quarks come in multiples of n/3 of this number. Okay, they come in either 2/3 of this value or 1/3 of this value. Let's pretend that let's ignore the quarks for now. Okay, when you take a higher level course, then you'll deal with that. Okay, and anyway, to deal with quarks, you have to actually go inside the nucleus of, well, you got to go inside the proton, and you got to go inside the electron. Okay, so let's ignore the fact that we have quarks for now, and let's just say the basic unit of charge is this value, and this value, and all other charges are some sort of linear combinations of those two. Okay.
Professor?
Yes.
How are the charges linear combination? Like, aren't they just multiples of these?
Well, what I mean is if I take 2 electrons and 3 protons, right? If I take 2 electrons, I'm going to take 2 times this plus 3 times that. That's what I mean.
Okay.
Right, because one's positive, one's negative. That makes sense in terms of how I said that?
Yeah, it is just like how many electrons there are and how many protons
Yes, it's just based on that.
in that material?
Yes. Right, so if you're taking 2 times this plus 3 times that, that's a linear combination of those two numbers. Granted, the magnitude of these two numbers are the same, okay? But when I'm counting the number of electrons and the number of protons, I got to take the number of electrons times this number plus the number of protons times this number. That's really, technically, it's called a linear combination. Okay. All right. Just give me 1 second. Okay. I'm just trying to adjust my screens. Just give me a second. All right. Charges add algebraically just like masses. Charges can cancel because you can have a positive charge and a negative charge. Masses don't cancel. Masses just add. Okay, because all masses are positive. But if you take 2 electrons and 2 protons, you take 2 times this number plus 2 times this number, you get 0. Does that make sense? I mean, it's a pretty basic thing. And that's the one thing that distinguishes charge from mass fundamentally, is that masses are always positive and they just add up to some number. I should mention that these particles do have mass. The mass of the electron, I mean, somebody measured them, not with a scale, but they measured them indirectly. The mass of the proton, and I usually quote them to 3 sig figs. The neutron is about the same value of mass. It varies at the next digit. The proton and the neutron are not exactly the same mass. Now let me put the charge of the neutron. Okay. Oops. Now, just to illustrate the idea of conservation of charge, if you take an electron and you collide it with this antiparticle called a positron, so that's an electron and a positron. If you slam them into each other at high enough energy, at least, and you can do this calculation because we already had relativity, at least 1.02 MeV, you'll produce 2 gamma rays, basically two quanta of light that go off in opposite directions. You actually have 2 objects that have mass. They slam into each other and produce 2 photons, no mass. Remember, from relativity, we learned that mass and energy are on the same footing. But what you notice here is that if you take the total charge of these 2 objects, the positron's positive, the electron's negative, you get 0. These photons have no charge. So you ended up with what you started with. And your energy is conserved. Okay, and you can observe this in the lab. So this is called pair annihilation, but there's also something called pair production, where you run this experiment in the opposite direction. You can actually have 2 photons interact to produce an electron and a positron. Both of those phenomena have been observed in the lab. Both of them also show that charge is conserved. So let me just say, before I start talking about the properties, the electrical properties of matter, and by the way, I'm going to be very simple-minded in terms of how I'm going to describe things here. Okay, even that picture you see there regarding the atom is not really correct. Okay, so we talk about atomic structure. Atomic structure, we can categorize them in terms of atoms, ions, and molecules. And they're all made up of protons, neutrons, and electrons. Protons, neutrons, and electrons are the basic particles that make up matter. Again, let's ignore quarks and things like that, okay? So let me start with an atom. A neutral atom. A neutral atom has the same number of protons as electrons. And I'm going to use the letter Z to denote the number of protons and electrons in an atom. So for example, the hydrogen atom has 1 proton and 1 electron. Again, this picture I'm drawing is not accurate. So you have a proton with an electron going around it. The reason why it's not accurate is because the electron is really a wave and not something going in a circle. Although the first model of the atom assumed that the electron was going around the proton in the atom. Okay. But realistically, we got to treat them as a wave. And so if you have something with like uranium has 92 of these protons and 92 of the electrons if it's neutral. And it has a bunch of neutrons in it. Okay, if you have an atom and you can vary the number of neutrons in it, then you have something called an isotope. You have different isotopes of an atom. For example, this is the hydrogen atom. You can have a hydrogen atom with a neutron in it. This is called deuterium. And this is called a deuteron. This is just a different isotope of hydrogen. The atoms are identified by the number of protons they have. So this has 1 proton and mass of 1 atomic unit. Okay, the mass of a proton is approximately 1 atomic unit. Oops, wrong way. So H21, I have 2 atomic units, and we don't count the electron because it's really light, and then 1 proton. And then there's another isotope of hydrogen that has 2 neutrons in the nucleus, and the proton. Now, just to give you an idea of the size of this thing, the nucleus the nuclear size is of the order of 10 to the minus 15 meters. Okay. The size of the atom is of the order of 10 to the minus 10 meters. So there's a lot of empty space between the proton and the electron in an atom. I mean that's a factor of 100,000. Okay, that's a factor of 100,000. Just scale it to our universe. Okay, scale it to our size and see what a factor of 100,000 means. So there's a lot of empty space here for the electron. Okay. Then there's materials called ions. What's an ion? Well, it's an atom with, for example, an electron removed. Suppose you take off the electron from the hydrogen atom, you have a proton. You have something with a positive charge. If you take off the electron, the total charge you have is positive. So then you would have an ion called H plus. You can add an electron to the hydrogen atom. If the hydrogen atom has an extra negative charge on it, then it's negatively charged. And so it's minus. And the question is, how high of a charge can you have on an atom? You can go in the lab, although this thing is going to be very unstable. You can go in the lab and produce a beam of highly charged uranium ions. Remember, uranium has 92 protons. Okay, so uranium has 92 protons. You can strip off 91 electrons. You can actually produce this in the lab. Each one of these numbers means you have some number of electrons removed. So 91 means you removed 91 electrons. So the total charge of this thing is going to be 91 times 1.6 times 10 to the minus 19 coulombs. Remember, the coulomb is the unit of charge. Of course, this is very unstable. It's going to want to react with anything. It's going to want to suck up electrons right away. Okay, but you can create that in the lab. On the other hand, if you wanted to add electrons to an atom, the most you can add, guess how many is the most you can add? It's only one. The most electrons you can add to an atom is one. At least to our best knowledge, we have never found an atom with 2 electrons attached to it in the gas phase, right? If you take an isolated atom, the most electrons you can add to an isolated atom is 1 electron. And in fact, there are some atoms in which you cannot add the electron. For example, here's a couple of them. Nitrogen and zinc. They do not want the extra electron, and so no one's ever discovered in the lab a nitrogen atom with the extra electron in it. And same thing for zinc. There's others. I just don't remember the other ones. Those are the ones that come to mind. Okay. Now, of course, if you have a bigger system like a molecule, you can find there is a possibility you can add another electron to it. Okay, so we also have molecules. What are molecules? Molecules are combinations of atoms. So for example, H2O. We all know about H2O, right? That's water. That's a molecule. They're just combinations of atoms. And whether we have water molecule or hydrogen atom, they each have their own electrical properties. And in some cases, some of their electrical properties are quite interesting. Okay. And if you remove an electron from this molecule, you form an ion. Okay. And I think in chemistry, some of these are called radicals, right? I forget.
Radical is typically, I don't think they call it charged, but like one that has uneven number of electrons. But it is, yeah, it can be charged, but radical, they usually just draw 1 electron for it.
They just draw one with an extra electron on it. Now I want to draw your attention to another type of system that's really been talked about maybe the last 30 years, but you don't always see it in textbooks. You don't see it in the physics books. I'm not sure if you see it in the chemistry books. You can take a hydrogen molecule, and you can do the same thing with atoms, and you can form a bunch of them, in one group, something like that. Okay, these are called clusters. You can do the same thing with carbon. You can take 60 carbon atoms into the shape of they will form a shape of a soccer ball. Okay, these are called clusters. Large numbers of atoms or molecules that are combined together. These are called clusters. And people have been studying them over the years. This one's famous. These are called buckyballs. Okay. And this kind of started the revolution in nanotechnology. Okay. So that's another type of matter. And again, they all have their own electrical properties. And something like this, you can add 2 electrons to. Okay. The problem with adding an electron is because the electrons are so far away from the nucleus, they're not going to be around, they don't want to be around each other. And the repulsive force is so great, it's very difficult to add the second electron. But you can do that with something much bigger, like a C60. And there are some molecules in which the doubly charged negative version of them do exist. At least they've been predicted. But not all of them have been found in the lab. Okay. Anyway, I just wanted to say a few things about the basic constituents of matter. And their behavior is what gives materials their electrical properties. However, when you form a solid with some of these, or you form a liquid, there's also an interaction between the molecules, or an interaction between the atoms that you also have to take into account that affects the electrical properties of the material. So what I want to say now is I really want to talk about 2 types of materials. Those that conduct electricity and those that do not conduct electricity. And again, my discussion is going to be very idealized for what we're going to be doing here. Okay, so I'm ignoring things called semiconductors. All right. So we have 2 items. Those that conduct electricity are called electrical conductors. And by the way, materials that are electrical conductors also are good conductors of heat, of thermal energy. Metals are good conductors of electricity. Why? Because in a metal, when you get a bunch of atoms together, whether it's aluminum or gold, the way they interact to form that solid, what happens is you end up with a lot of the outer electrons from each of the atoms really being loosely bound to each of the atoms. You actually have a lot of a lot of electrons that are free to flow. Okay. So when you take a bunch of atoms and you form a solid out of them, the nature of the atom-to-atom interaction causes the outer electrons in the conductor to be very loosely attached to any individual atom. So the electrons, you can think of it as a fluid that can flow through the conductor. And the electrons carry the electrical energy. And just to give you an idea of how this works, I have a can, all right, and I'm going to, hold on, I got to change my, just give me a second here. Can you see this little table?
Yeah. Yes.
Okay, I'm going to take the can and put it, it's not going to work very well because this can has a label on it, unfortunately. Although the can has no coating on it, that's why I'm using it. So, it's uncharged, okay? The can is completely uncharged. Actually, you know what? Let me zoom in too. Let me zoom in some too. And maybe it's a little blurry. Okay, so I'm going to charge. All right, this is how I'm going to charge, and I'll talk about what's going on here in a minute. I'm charging my PVC rod. I'm transferring electrons to the PVC rod. And I'm attracting the metal can. You all see the can get attracted? No matter whether I charged a positive rod or a negatively charged rod, the can will always be attracted. So I guess the question is, why is that? Why will a can always be attracted? What do you think? Yeah, in the case where I made this negatively charged, then when I bring the rod close to the can, the electrons in the can are going to want to run away to the other side of the can. That leaves a net positive charge, and so what you have is a positive charge near a negative charge. They attract. If my rod was positively charged, I brought a positively charged rod by the can, then the electrons in the can would be attracted to the positive charge, bringing towards this side of the can an excess of negative charge, and then you still get an attraction. Does that make sense? So no matter what the sign of the charge is on my rod, you're always going to get an attraction with the metal can. That illustrates how easy the charge can flow in a metal. And I'm assuming an ideal conductor, okay? I'm assuming ideal conductor when I discuss this. And then I'm also going to talk about the opposite, the insulators. What's an insulator? An insulator is a material in which the electrons cannot flow at all. Ideally, they don't flow at all, but we can say that they don't flow very easily. Most materials, most insulators, have a property called polarizability, in which the average charge of the average location of the positive charge and the average of location of the negative charge can be separated, forming something called a dipole. Of course, these materials are called dielectrics. So materials have this thing called polarizability. Insulators have a property called polarizability, in which you can separate the positive and negative charge within the material to form a dipole. And then it will exhibit electrical properties. Now, some materials already have the negative and positive charge separated. Some materials are already polarized or polar. Can you think of something that's polar?
Water.
Yeah, water is a polar molecule. And so you would see electrical effects be more pronounced with water than you would have something that's not polarized. Water has something called an inherent dipole moment, and I'll define the dipole moment in a little bit. And so it will exhibit electrical properties. Okay. So even though material is an insulator, it will still exhibit some electrical properties. So let's take a charge object and bring it near an insulator. What happens? Okay. If you take a charge object and bring it near an insulator, like rubber or wood, whatever, let's say I take a rod, it's negatively charged, and I bring it near this insulator. What happens? Well, the molecules that make this up, they don't like these electrons. And so what's going to happen is the distribution of charge will change. You'll end up having with more positive charge here and the negative charge there. When you get the average position of the negative and positive charge to be separated within the molecule that makes up the material, you have formed a dipole. So this separation of charge is called a dipole. And we quantify it. These two are equal and opposite charges, and they're separated over a distance L. And so the dipole is defined in terms of the separation we'll call L and the charge of these guys. So we define the dipole moment as a vector Q times L. Well, Q is the magnitude of these two charges. L is the vector that goes from the negative charge to the positive charge. Okay? And this quantity plays an important role when we're trying to model systems. Okay. So I'm showing you a picture of an insulator that's polarized already. The atoms or the molecules that make up the material have dipoles inherent in it, but the dipoles are oriented randomly. If I take a charged rod and bring it near the polarized material, then what happens is the dipoles will tend to align themselves towards that charged rod. Now, the picture I'm showing you is exaggerated. Okay, when I say there's a tendency to align towards that charged rod, it doesn't mean every single dipole will align itself towards that rod, but a majority of it will be. Okay, so my picture is an exaggeration. Not every single dipole that's in the material will align itself like you see in that figure. Okay, but the idea is to illustrate what happens. So, one more demo, and then I'll go on. This might be a little bit more dramatic. So let me get my table out here. So you saw that when I have a metal object, like a can, it's uncharged, it will always be attracted to something that's charged. What about an insulator? So when I do this on campus, I have a petri dish. I don't have a petri dish here, so I had to use I actually have an upside down strainer. And I have a board. The hardest part of this demo is to balance the board on the strainer. Okay, you guys see the board balanced on the strainer?
Yeah.
The board has no charge on it. I'm going to take my PVC rod and I'm going to charge it up. Let's see what I can do, if anything, with this big board. Nothing. Because these demos never work when you do it in class. I do it beforehand. Do you see the board moving? Did you see the board change direction? All I did was bring this rod by the board, nothing magic. And the board rotated. Okay, I got the board. So what does that mean? Even when I have an insulator, if I bring something charged near the insulator will be attracted to that charged object. That's always the case. Let me see if I can get it to go back. Okay, it rotates a little bit. Okay? Let me go back and change. Let me change my blinds too because I got too much sun coming in. Okay, that's better. You guys can see the board okay?
Yeah.
Okay, all right, good.
And Professor?
Yes.
Would the rate of would the rate of motion of the rod change if the rod was wet?
Yes.
Okay.
Yeah, I mean, the rate at which it would turn would depend on how well I can polarize the rod, how well I can polarize the charge in the rod. So yeah, you're right. That's a good observation. Now, in order for me to get that to work, I had to balance the rod on that bowl, because if I just put it on a table, the force would be too small for the rotation to occur. I'd have too much friction. But I had to put it on something round, so it was only basically the board was basically sitting on one point, and that made it easier for it to rotate. So let me talk about the two types of charging. There's charging by contact, and there's charging by induction. I kind of talked about what charging by induction means last week. So charging by contact means this. Basically, you take, and I hope your piece of fur is better than mine, and your kit. So basically all you do is you take the piece of fur, you put it on the rod or whatever material you're trying to charge, and you just rub them together. And the question is that due to friction? Because you will see a lot of websites say, well, let's do the friction. So Chase, you can use the wool too. There was, I think, if you're having trouble with the fur, the wool might work okay too. There should be a little square like this. It might not be this color, but I think one of these came with it. Okay. So the question is this charging by, is it friction causing this? And you'll see a lot of websites just say it's charging by friction. And you got to be careful when you say that, because I can take two pieces of fur and rub them together. There's friction between them. You think you're going to transfer charge? No, you're not going to transfer charge. The reason why charge is being transferred is because the two materials have opposite electrical properties. One likes to pick up the electrons, the other one likes to give them off. And in fact, people have done experiments over the years, and they've come up with something called a triboelectric series. And the triboelectric series basically measures whether a material wants to pick up electrons or give off electrons. And so if you have two materials that have the same triboelectric rating, you can rub them together till you're blue in the face. You're not going to transfer charge. So to say that the charging by contact is really due to friction, it's kind of misleading. What friction allows is for the atoms to interact with each other. The reason why it's charging is because the two materials have different electrical properties. They have basically opposite electrical properties, if I can say it that way. One wants to give off the electrons, one wants to pick them up. And by rubbing them together, you're giving the two materials a way to interact with each other so that charge can be transferred from one to another. Of course, there's going to be friction there. But again, if you have two materials that have the same properties electrically, they have the same rating in the triboelectric series. You can look this up online. They have lists. They assign a number to various materials like transparencies, styrofoam, etc. Most of them are actually like picking up electrons. Most of the materials you'll see like picking up electrons. Okay. You'll see the list. And if you find two materials that have the same properties and you rub them together, you're not going to transfer any charge. Okay, so be careful with this. And normally when we do the lab on ground, we do an experiment with tape. We have you do an experiment with tape to prove that. Although it's kind of hard to do it at home, so I kind of eliminated that. Okay, I actually simplified the lab a lot that you're doing, because one of the things we also do in this lab when we're in class, when we're face to face, is you get to play with a Van de Graaff generator and you get to electrocute. I mean, you get to play around with it, the device. Okay, and yeah, you might electrocute yourself a little bit, but it doesn't kill you. Okay. When you have a conductor, so let's say this is a conductor, and let's say you just have positive and negatives everywhere randomly. And then you put a positive charge or a negative charge near it. I guess I'll use negative because that's the easiest one to work with. What happens is when I bring this charge near the conductor, and it's isolated, when I bring this negative charge near the conductor, the electrons in the conductor are going to want to run away from this negative charge. And so they're going to move to the opposite side, leaving the front side positively charged. And what I mean by positively charged means there's going to be more positive charge here than negative charges. And again, this picture I've drawn here, and the picture you see in the slide is an exaggeration, but it's drawn that way to illustrate a point. That when you bring a negative charge near the conductor, the electrons are going to want to run away, leaving an excess of positive charges. So essentially, you temporarily induced charge on both sides of the material, right? You have a net charge here and a net charge here. So you're going to see a force of attraction between these two materials, just like you saw with the can. Now, what if I take a wire and I touch it to ground, like the water pipe in your house? And by the way, the symbol for ground is this. That's the symbol for ground. So let's say I put one finger here and then the other finger on the water pipe. What's going to happen? Well, ground is like a sink, right? When you let water go down your sink, it's like a sink or a source of electrons. So when you bring this negative charge near the conductor, these electrons are going to want to run away, so they run away to ground. And if you still keep this charge here and then disconnect your ground wire, you've permanently induced charge. That's called charging by induction. I've made this positively charged now. Okay. That's what you're doing with the electrophorus. Right? That's what you're doing with the electrophorus. There's other ways. There's other ways to charge by induction. Let me give you another example. Suppose I have. Let me check my time. Okay. Suppose I have a conductor with an insulator. So this top piece is a conductor, this is an insulator. And this is a conductor. And I take a rod and just for fun, we'll make it positively charged. Just to be different. Of course, what's going to happen? Well, the electrons are going to come towards the side that's nearest the positively charged rod, and then this side will be positively charged. Because remember, only the electrons can move around. Now, suppose I take another one of these devices. It's a conductor. And I touch it to the first one. What do you think is going to happen? What do you think is going to happen to the electrons in this one? The electrons are going to go here. And then they're going to leave this positively charged. And then I just separate them. I just pull them apart. This will be negatively charged, that'll be positively charged. So I've actually charged both of them by induction. So basically charging by induction, what you're doing, you're not rubbing things together, okay, to charge the object, okay? All I did was I brought this in contact with this guy, with the purple guy, and then charge got rearranged. I pull them apart, and then I have two materials that have opposite charges. That's another way to charge by induction.
So negative charges go to the ball on the. Then after the charges have transferred, does the two spheres repel each other?
Well, they would attract each other, right? Because this is negatively charged, this is positively charged.
Yeah, but like the positive that is first one to the right, like that side of it would repel the positive charge on the second sphere, right?
Yeah, it would be hard to know. I mean, because of the fact that the way I've drawn an exaggerated picture, the point is I'm going to have an excess of negative charge here and an excess of positive charge here, but it's hard to say what would happen here. Right? Because when I pull them apart, what will happen within maybe 10 to the minus 16 seconds, the negative charge in here will redistribute itself. So, you know, you might be correct, but you'd have to be able to see it within 10 to the minus 16 seconds.
Yeah.
Because the effects are very fast. Okay, so and really there's not really much for me to say about the lab, but I do have a question for you. And I have set up a poll. Do you guys all see the poll? So,
Yeah.
somebody does an experiment. And I guess there's only 6 of you here. Oh, well. So somebody does an experiment. So you have 5 styrofoam balls. They're suspended from insulating threads. And several experiments are performed on the balls, and the following observations were made. Ball A attracts B and repels C. Ball D attracts B and has no effect on E. And then a negatively charged rod attracts both A and E. So what is the charge on each ball? That's the question. So go ahead, think about it, and then answer the question. It's like an SAT exam question. Normally, if we were face-to-face, I would have you guys talk to each other about it, but I can't do that here. All right, I just need 2 more people to respond, and then we'll be set. Okay, so I have everyone's response. If you folks feel confident in your answers, as confident as can be. Okay, I'm going to end the poll. I'm going to show you the results of the poll. It doesn't say who answered what, so don't worry about it. So these are the results. So I have a distribution of responses. So yeah, I mean, if we were face-to-face, it would have been better if you guys were able to talk to each other. Okay, I'm going to stop the sharing. Let's discuss the, let me end this poll here. Just remember the answer you chose. Okay, so let's talk about this. So it says ball A attracts B. That should tell you that they have opposite charges, correct?
Mm-hmm.
Okay, so A and B have opposite charge. And then A repels C. So that means they have the same charge. Correct? I'm just writing down the list. Then ball D attracts B. Okay, so but here's the key. D has no effect on E. What does that mean? What does that mean? Yeah, it means E is neutral. What about D then? And you're right, E is neutral. What about D though? Now be careful, because what did I do with the two demos? What does the two demos show? And you're right, Kathleen. The two demos show that an uncharged object is always attracted to a charged object. So even though ball D attracts B, doesn't mean D is charged. The only way these two have no effect on each other, the only way, is if neither one has charge. So D and E it has to be true that D and E have no charge. Now, a negatively charged rod attracts both A and E. So that tells you, number 3 tells you that A has to have the opposite charge of the negatively charged rod. So basically they're positive. I'm sorry. A is positive and C is positive. D and E neutral. If A and B are opposite, that makes B negative. So that's the answer. Are we okay with that? Okay, so let me show you the lab itself. So let me switch from my PowerPoint to my Word document. Oops, let me make that much bigger. Okay. Okay, so there's 3 parts to the lab. Normally when we're face-to-face, this actually has 5 parts. And one of them is the fun part's missing. So you're going to create a video, whether it's on YouTube or in Canvas Studio. And really what you're going to do is observe and explain. And I list the equipment you need. And some of the equipment you've already built. You've already built the electroscope and you've already built the electrophorus. That's what, I mean, assuming. And you just need some fur or silk or wool and a couple of other things from your lab kit. Some of the things you get from home, like salt and sugar. So I do list the things that have to be returned. And I think Tyler put in the lab kits the things that need to be returned also. In part 1, there are 3 effects that I want you to play around with. They can all be explained the same way. And what I would like for you to do is video one of them and explain it. Okay? So just pick one of those 3 phenomena, the one that's easiest for you to do, and just video it and explain it. Okay, explain what is happening. So what I want you to do is to explain in terms of concepts I just described. Are the charge, when you bring the negatively charged rod in, does the charge get polarized? Do you form dipoles? Use those terms, use those key terms that I used in my presentation today. Part 2, that's where you're going to do experiments with the electroscope. And I forgot to remove a couple things. You're not using the glass rod. Okay. So for the first one, you're only doing it with the PVC rod. Okay, just make a note of that. You're only doing it with the PVC rod. You're not include. You don't have to do the glass rod. I will make a change. I will make a edit to this document. The glass rod is too much of a pain. It doesn't work very well. So you're going to just show how the electroscope works. Okay. I think that this is self-explanatory. This is very qualitative. Observe and explain. So there's really not much for me to say. And then same thing with the electrophorus. You can, instead of using styrofoam with the electrophorus, you can use saran wrap. You can try saran wrap. You should try different things. You can try transparencies instead of styrofoam or the saran wrap. Just experiment and then just do whatever works best for you. And you're going to try different things. You know, what happens when you change the distance between the charged styrofoam and the plate? What happens when you increase the distance? And so can you repeat the process over and over again? Those are questions to answer in these videos. Okay, so I want these to be demonstrated and explained. And then I have a rubric for the experiment. So go ahead and follow that rubric. That's what I'm looking for in this experiment. So this video will be a little bit longer. I'm hoping that it's under 10 minutes. I did have a student last semester turn one in that was 40 minutes, but that's because the student did the experiment while they were filming it instead of just trying things first and planning things out. So it was very inefficient. You don't have to make a single video if you don't want to. You can make multiple videos if you feel more comfortable making multiple videos. It doesn't have to be a single video. Some people are good at editing. They'll make multiple videos and then bring them together into one. You don't have to do that. Okay. Does anybody have questions on this? Or concerns? So next week, well, I'm hoping you bring questions on this next week, but next week, to prepare for the following lab, the lab after this one, you're going to be doing something called a multimeter quiz. You're going to learn how to use a multimeter, which is in your kit. And so I actually have to lecture on material from chapter 27. It's really basic stuff. It's probably the easiest chapter we'll cover in the whole course. It's just about how you can get electrons to move in a wire. Okay, so that chapter is fairly straightforward. So I'm going to give a lecture on chapter 27 and talk about how you make measurements with the multimeter. Okay, so that's next week. So I'll probably have at some point send you an email saying read chapter 27. I mean, what I mean by that is just skim through chapter 27 so you know what I'm going to say. You don't have to read it thoroughly. You should only read it thoroughly until after I've discussed the material. Okay, we all okay then? No questions? I'm going to run off to my 9:30 class then. We'll see you at 2.
Thank you.
All right. Oh, you have a question, Chase? Oh, I'm sorry. How strong should the effect be for electroscope? So Chase, did you? It really depends on how much charge is on the rod. Did you try to charge the electrophorus and then also bring the electrophorus by the electroscope? Because that one's more pronounced. And I realized with the rod, it might be just a little bit. But I think with the electrophorus, it's significant. And maybe you might want to show both in your video. Okay, cool. Okay, so I'll see you folks at 2 then.
Thank you.
All right, you're welcome.